Hello everyone, I'm Qing Zhan from Netherlands Institute of Ecology. Today I'm going to present my study on the impacts of heatwave on eutrophic versus oligotrophic sediments. The title of my study is the effectiveness of phosphorus control under extreme heat waves, implications for sediment nutrient release and greenhouse gases emission. My supervisor is Dr. Lisette de Senpong-Donis. My presentation will start with a short introduction of the background information, which leads to the research questions that we want to address. Upon these questions, I'm going to introduce our experiment design. Then I will present our results and discussion, mainly from two aspects: nutrient release and greenhouse gases emission. Finally, I will summarize the implications for eutrophication control and climate change from our study. We all know warming can lead to more mineralization and respiration, therefore affecting the nitrogen, phosphorus, and carbon cycles. But we are not sure about how the warming impacts differ in eutrophic system with high nutrients versus in oligotrophic system with no nutrients. In this study, we investigated these two aspects of global change, eutrophication and climate warming, identified as two of the biggest pressures on aquatic ecosystems. We focused on the fluxes between sediment and water, which for shallow waters play an important role in the phosphorus, nitrogen, and carbon cycle. More specifically, in this study, we want to investigate the effect of extreme heat wave on the heterotrophic processing in eutrophic, meaning high nutrients, versus oligotrophic, meaning low nutrient systems. We want to, by the end of this study, answer mainly three questions. First, will heat wave increase sediment phosphorus and or nitrogen releases? Second, can Phoslock reduce the potential heat wave induced nutrient release by forming physiochemical barrier on sediments? Last, will greenhouse gas emissions be mitigated in oligotrophic systems through decreased nutrient availability? A widely used phosphorus adsorbent is Phoslock, a lanthanum modified clamp designed to removing filterable reactive phosphorus from water column by forming insoluble lanthanum phosphate complex. We conducted a 3-week sediment incubation experiment to study the heatwave and oligotrophication interactive effects. In total, we have 36 sediment cores. We split them into 3 groups, such that 12 cores were treated with Phoslock, 12 cores were treated with the bentonite clamp, which is the clamp in Phoslock, and the other 12 cores left untreated with any solid phase solvent. Hereafter is referred as SPS. In the second week, half of the cores in each SPS treatment was exposed to a 1-week heat wave by heating the water up to 30 degrees, while the other half stayed at the ambient temperature 20 degrees. In the last week, so the third week, the heat wave treatments were cooled down to the ambient temperature again, leaving 1 week of post-heat wave phase to study the transient or persistent heat wave impacts. As the temperature data shows, half of our sediments which include 3 SPS treatment units, were subjected to 30 degrees heat wave during the second week of our experiment, whereas the other half were kept around 20 degrees throughout the entire experiment period. The result of principal response curve of multiple variables including oxygen, pH, phosphate, ammonium, nitrate, methane, carbon dioxide, and nitrous oxide suggested a limited influence of bentonite treatments, indicated by the proximity among the green curves for control and then the blue curves for the bentonite treatments. In the oligotrophic systems by Phoslock, shown as the orange and red curves in the graph, it differed strongly in responses than the control and bentonite groups. Among the multiple variables included in this analysis, phosphate was the most important contributor to the system variances, as indicated by the z-axis on the right side. The dissolved oxygen dynamics over time indicated that our systems switched from a DO-depleted condition at the beginning of the experiment to a less reducing condition by the end of our experiment, which was also supported by our sediment redox potential profiles. The DO results showed that heat wave can enhance respiration and therefore oxygen consumption, indicated by the lower DO concentrations in heatwave exposed treatments. However, we did not observe a significant difference in DO concentration between the eutrophic and oligotrophic systems. The phosphate data shows that in our eutrophic systems, there were a continuous internal phosphorus release from the sediments, whereas a heat wave exposure did not significantly change this trend. In our eutrophic systems, however, a persistent phosphorus release by circa 0.05 microgram per meter was detected when exposed to heat wave. From the sediment phosphorus fraction data, we speculate that heatwave induced a transformation of redox-sensitive phosphorus into pore water phosphorus, indicated by the lower redox-sensitive phosphorus fraction and higher poor water phosphorus fraction in the heatwave exposed groups. The decreased dissolved oxygen during heatwave could need more immobilization of redox-sensitive phosphorus. In our eutrophic systems, however, this elevated poor water phosphorus in heatwave exposed treatments did not translate into higher phosphorus release into water column, which indicated that the internal eutrophication override the impacts of heatwave. In agreement with our speculation on dissolved oxygen that our system switched from a very reducing system to a less reducing system, the dominant form of nitrogen changed from ammonium to oxidized nitrogen, that means nitrate and nitrate, during our experiment period. Heatwave exposure enhanced the nitrification and the nitrogen release, but a reduction in phosphorus concentration had no effect on the nitrogen level. The measurements of diffusive greenhouse gases concentrations, including carbon dioxide, methane, and nitrous oxide, along our experiment period, supported that exposure to heat waves enhanced greenhouse gases emissions, whereas the persistence of heat wave impacts is different in individual gases. For instance, as we can see in the graph, it seems that the effect, the heat wave impacts on carbon dioxide is transient and disappear after the heat wave period. But we still detect heat wave impacts after the heat wave in both methane and nitrous oxide with different direction. A potential reason for that is the different substrate availabilities in our systems for the respective gas production. On the other hand, a reduction of nutrient availability by Phoslock, however, cannot influence the greenhouse gas emissions. Our study indicates that in eutrophication control by Phoslock, achieved reduction of phosphorus can be persistently impaired upon heatwave exposure. Hence, nutrient abatement efforts might need to be intensified to compensate for the negative impacts of extreme climate events. Regarding climate change, phosphorus reduction does not need to lower greenhouse gas emissions. Therefore, alternative strategies that target reduction in organic load should be explored for mitigation of greenhouse gas emissions. Before closing my presentation, I want to use the chance to acknowledge all the people who make this study possible. Qing Zhan, who did the experiment, Dr. Han van der Heest from Amsterdam University, who helped with the sediment redox potential measurements, Dr. Michael Lenning from Wageningen University, who gave supervisory in this experiment, Wendy Beckman, Lucassen, and Nico Hemsing, and Dr. Mary Muser for their assistances in the experiment, Dr. Aninas Verhaert from the Nijmegen University, and Dr. Christoph Hensingen for their help on the gas measurements.